Welcome to scale drawing and similarities. So these are just two topics, but they are short and they are easy. So the key concept in scale drawing, it's about representation. So you can have maybe maybe a plot. So you'd want to represent that plot on a piece of paper. Okay, so that's what scale drawing is all about. You need to come up with a scale. So imagine you have this plot. Okay, so now whatever dimensions of this plot, we can say it's 20 by 10. So you want to represent, this is 20 meters by 10 meters. So you want to represent these dimensions on a small piece of paper, which is maybe 15 centimeters, maybe 15 centimeters to 30 centimeters. Okay, so you can't draw the actual plot on the piece of paper. You need to scale down. So scaling down means these 20 meters must be presented by a small number, so that when you draw it, it's going to fit on the piece of paper. And also this 10 meters must be represented by a small number, so that when you draw these two, you can represent the plot on a piece of paper. We can say maybe 2 centimeters and 2 centimeters and maybe 1 centimeter here. Okay, so my pen is misbehaving. Okay, so anyway, 2 centimeter on top and 1 centimeter here. So what you can see is this 20 meters has been scaled down and this 10 meters has been scaled down, but they have been scaled um, um they have been scaled down using a same scale. I want to find the different way of saying this. So 20 has been represented by 2, 10 by 1. Okay, so maybe we can say 20 has been multiplied or has been divided by the same number as 10. For example, we can say 20 should be divided by 10. So 20 divided by 10 will get 2, and 10 divided by 10 will get 1. So we can say maybe both of them have been divided by 10. So whatever measurement we have on the actual plot, we have to divide it by 10. Okay, so there's always one number which we use to scale down something. Okay, so that number is called the scale factor, and the scale factor is the basis of scale drawing. Like whatever calculations we're going to be doing, they're going to be centered on scale drawing, on scale factor. Okay, the opposite is true. You can have a plan on a piece of paper. So you can have a drawing here on a piece of paper, then they can ask you to reproduce or to make the actual thing from that plan. So you have to know that small measurements, they have to be transformed into bigger measurements by multiplying them by or with a scale number, with a same number called a scale factor, which is going to be presented. So the formula for scale factor is map distance over actual distance. So by map, it can mean paper distance or graph distance. So by map, we just mean what is recorded, what is written. So but we're going to be using the word map. So map distance over actual distance. Actual distance is the actual distance of the real thing, not the thing that has been drawn or that has been written or that has been graphed on a small piece of paper. Okay, so the scale factor is stated usually in terms of ratios. So the scale factor is usually stated in terms of ratios, like so: 2 to 200,000. So the first number, the 2 represents the number on a piece of paper or graph or a drawing. Then this big number or the number on the right represents the real thing. Okay, so the one on the left represents the map distance and the one on the right represents the actual distance. Then when they write a scale like this, one thing you should notice, these two numbers are in the same unit. So if you use centimeters for the actual for the map distance, then the actual one should also be in centimeters, meaning that it should be 200,000 centimeters. If you use kilometers on a piece of paper, then even this one should be in kilometers. So on the left, it's the map distance. On the right is the actual distance. So this can be written in this format as 2 over 200,000. Map over actual. Map over actual. So here's an example. A map is drawn to a scale of 1 to 1000. Given that a river has a length of 5 centimeters on the map, what is its actual length? So they have given us the length on the map. They want the actual length of this river. Second, given that a building has an actual width of 250 kilometers, what is the width on the map? So they have given us the actual width. They want us to know the width on the map. So here's the solution. So our K from what we have been given here, it's 1 to 1000, which is this. Okay, so once you have the K, everything becomes easy. Remember, the formula for K is map distance over actual distance. So on the left, we're going to put 1 over 1000. Then for question 1, we've been given map distance, we're looking for actual distance. So on map distance, we're going to put 5 centimeters. On actual distance, we can put X or anything. Then we solve for the unknown. So we're going to have this. When we cross multiply, we're going to have 5000 centimeters as the actual distance. So the same question, but this time concentrate on question 2, which says, given that a building has an actual width of 250 kilometers, what is its width on the map? So this is opposite. The actual building has a width of 250 kilometers. What is its width on the map? So here's the solution. So K, we know it's this one, and the formula for K is map distance over actual distance. Map distance is the one we're looking for. Actual distance is 250 kilometers. Okay, so the K, we write it here. Map distance X, actual distance 250 kilometers. When you do cross multiply, we're going to get 1000 times X is going to be 1000X. 1 times 250 kilometers is going to be 250 kilometers, like so. Okay, so we can divide both sides by 1000. When we do that, we're going to get 0.25 kilometers. So the distance of the width of the building on the map is 0.25 kilometers. Now this is an interesting example. During an exercise on graphs of polynomials, Berliner has been instructed to use a 2 centimeter to represent 5 units in the x-axis and y-axis. So this student of mine, Berliner, has been instructed to use a 2 centimeter to represent 5 units in the x-axis and also y-axis. Okay, that's what the question is saying on a graph of polynomial. So given that she wants to plot the point 20, 30, how many centimeters should this point be from the origin along 1, the x-axis, 2, the y-axis? This might look complicated, but this is what you always do when you're doing any question that involves graphs in paper 2. So this question has given us that the scale that we should use is 2 centimeters to represent 5 units in both axes. Okay, then she has this task. She wants to plot 20, 30. Okay, remember the 20 is the x value and the 30 is the y value. So how can she plot this? Okay, so the easiest way she can is to know what 20 represents. What 20 represents in terms of centimeters. 20 are units. These 5 units here, they should be represented by 2 centimeters. So 20 units are going to be represented by how many centimeters? Once she knows how many centimeters, she can get her rule. then she put it from the origin, then measure the centimeters that she has gotten, and where the rule is going to okay, let me just demonstrate this. Let me just get my pen. So I've gotten my pen. So this is a graph. Okay, so here it's the origin 0, 0. So now she wants to know where 20 is going to be. Okay, so the easiest way she can know where this 20 is going to be along the x-axis, since this is the x value, she has to know how many centimeters this 20 represents. They have said 2 centimeters represents 5 units. Okay, 5 units. So 20, these are units. 20 units are going to represent what? That's the question. 20 units are going to represent what? So once she knows how many centimeters are going to be represented by 20 units, she can just get a rule and put it here. Let's say it's 3 centimeters. She identifies where 3 centimeters is. If 3 centimeters is here, so she's going to put a mark here, knowing that this is where 20 is. She'll do the same in the y-axis to know how many centimeters are going to be represented by 30 units. Once she knows that, okay, this is where the 30 units are, or the number of centimeters that are equal to 30 units are here, then she will know that it's here. So where the two are meeting, that's where her point should be. Okay, that's the idea. Now let's go into the actual mathematics. So sorry, I've written here and it's difficult to rub. So our K, as we know, is map distance over actual distance. So map distance is 5 units. Okay, then the actual distance is 2 centimeters. Okay, so how do you tell which one is map distance, which one is actual distance? So on a map, on a graph paper, we use units to represent measurements. Okay, but in reality we know centimeters. Okay, so this is difficult to understand if you view it in the sense of the actual distance and the map distance, but basically the boxes on the graph paper are units, so those ones are going to represent map distance. Then the one on a rule that we're going to be using to locate the points are the actual distances. Okay, so K is equal to 5 units over 2 centimeters. So this is a scale factor. Okay, so what can we do now with this information? Can we know what they're asking? Okay, how many centimeters should this point be from the origin along the x-axis? So we start with the first part. So the scale factor, like we agreed, is 5 units to 2 centimeters. Okay, so what we do is, to know how many centimeters are going to or are represented by this 20, what we do is we write like we did before, the formula for scale factor, which we know is map distance over actual distance. But the K, we know it's 5 over 2 equals map distance. What's the map distance? The map distance, like I said, are these units. So we have 20. Okay, actual distance, which is the centimeters we're looking for, we don't know, so we write x. Okay, so now we can cross multiply. 5 times x is going to be 5x. 2 times 20 is going to be 40. Okay, then we can divide both sides by 5, maybe this side by 5. Okay, so the 5 will go, will remain with x here. So where is this 0 coming from? Sorry, it's supposed to be 5 there. Sorry for confusing you. So 40 divided by 5 is going to give us 8. Okay, so 8 centimeters are the ones that are going to represent 20. So when you go on the graph, okay, so we have to put our meter rule here. Okay, not our meter rule, our 30 centimeter rule. So our 30 centimeter rule, we make sure that it's 0, it's on the origin. Then where 8 centimeters is, if it's here, then somewhere here, that's where our 20 is. Okay, so we do the same concerning the y-axis. So let's go to this number 30. So for the y-axis, we do the same again. Scale factor we know, so we're going to write scale factor, which is 5/2, equals actual distance, it's 30. I mean map distance is 30. Okay, then actual distance is x. So when you do cross multiply, 5 times x is going to be 5x, then 30 times 2 is going to be 60. Okay, divided by 5, divided by 5. So this will go 60 divided by 5 is going to be 12. So 12 centimeters. Okay, so meaning that on our graph, let's say here is where we had our 8 centimeters. Then we have to put a meter rule here. Okay, making sure that the origin, that's where our 0 is. And if our 12 centimeters is here, it means our 30 units are here. So we can just make sure that where this and this meet, which is here, that's where our point 20, 30 is. So this kind of question cannot come. It's not paper 1 question, but I was teaching for those who have issues with identifying points when doing graphs. So in case you're interested, and especially if you're in my class, we can learn more about this method as we are doing questions, especially those questions with decimal points, which give some students some trouble. But basically, this is the application of scale drawing. So with that information, we can now go to areas and volumes. Okay, given a foundation for a given house, what if we scale that house, we scale it down, we want to draw it on a map? What's the relationship between the actual area and the scaled version of the area? That's what we're going to discuss here. It's actually simple. So given a scale factor k, for areas, square it before using. That's the rule. Okay, so if they have given you a scale factor k, if you want to compare two areas, you have to square the scale factor. For volumes, you have to cube the scale factor. So in cube the scale factor, you can use it, but the usage is the same as you're going to see in the examples. So let's take a look at an example. So a plan for a house is drawn to a scale of 2 to 50. Given that the actual area of the floor is 100 meters squared, find the area on the map. So the actual area is 100 meters squared. They want us to find the area on the map. The second question says, given that the volume of the house on the plan is 300 meter cubed, find its actual volume. So normally I would recommend that when normally you are going to be given a scale factor or the ratios which are in lowest terms. If they're not in lowest terms, then take them to lowest terms. It's going to be easier for you to solve, especially if it's in paper 1. So we'll start with question 1. What do we do? So the first thing is to remember that k for areas is k squared, or for you to use your k to find the area, you have to square the given k. Okay, so the 2 over 50, which is our k here, remember how we get k, 2 over 50, we square it. So when we square it, we're going to get actually before square it, you can reduce to lowest term so that it becomes 1 over 25, like I said, so that it is easy for you to do numbers. Imagine if this 50 multiplies with a number, you're supposed to get a big number, but 25 will give a smaller number. So it's always better or advisable to work with smaller numbers. So what I've just done, I've just reduced 2 over 50 to lowest terms. So when I square 1, it will become 1. When I square 25, it will become 625. So this is the K to use. Okay. Now you have to note that the scale factor 2 to 50, 2 is what is on the map, 50 is what it represents in reality. Okay, so meaning that on top we're going to be putting numbers that are on the map, then on the bottom numbers in reality. So the question says, given that the actual area of the floor is 100 meters squared, so the actual area is 100 meters squared. So they want the area on the map. So remember, map distance over actual distance. So this side we're going to put our k, which is 1 over 625. I mean our k squared, which is 1 over 625. Then on map distance, that's what we're looking for. In this case, we're not looking for distance, it's area. So the best way actually to write this is map area over actual area. Okay. So on map area, it's what we're looking for. So we're going to put x. On actual area, we're going to put 100. So we're going to have 1 over 625 x 100. When you cross multiply, we're going to have 625 times x, 625x. 1 times 100, it's going to be 100. Okay, we can divide both sides by 625. When we do that, we're going to get 0.16 meters squared as the area. Okay, 0.16 meters squared. So of course in paper 1, if you don't want to have issues on how to get this, you can leave it as a fraction. It's okay. So we'll go to the second question. So we're looking for the actual volume. In this case, we've been given the volume on the plan. Okay, so K for volume is K power 3, remember? So we have K 2 over 50. We have to power 3 2 over 50 for us to get the K to use for volumes. So for volumes, like I've said, so we're going to cube 2 over 50, and it is advisable to reduce the scale factor. So if we reduce the scale factor, it's going to be 1 over 25 power 3. So 1 power 3 is 1, 25 power 3 is going to be 15,625. Okay, so this is the K we're going to use for volumes. So remember, K power 3 is map volume over actual volume. So what's the map volume? The map volume is 300 meter cubed. The actual volume is the one we're looking for. Then the K power 3 is this one, 1 over 15,625. So when we replace K power 3 here, map volume and actual volume, the one we're looking for, when you do cross multiply, 1 times x is going to be x, 15,625 times 300 is going to be 468,007. Is it? It's 4 million actually. Yeah, so it's going to be 4,687,500 meter cubed. So this is the actual volume for that given house. So we go to similarity. So we're going to end with similarity. So the scale factor of two shapes that are similar is found by comparing corresponding sides. Okay, so if you have been given two shapes, and if someone says these two shapes are similar, your job is to identify sides that are corresponding. Okay, once you identify those sides that are corresponding, you can use them to come up with a scale factor. For example, given that triangle ABC is similar to triangle PQT, then so we have ABC and PQT here. So normally you can tell which sides are corresponding just from the English. Okay, so if they say ABC is similar to PQT, the way they have written the letters, that's how you can tell which sides are corresponding. So the first letter is A, the second letter is B. Here, the first letter is P, the second letter is Q. So it means side AB and PQ are corresponding. Means that this side AB and this side PQ are corresponding. Okay, again you can look at BC and QT here. So BC and QT, as you can see, B is the second letter, C is the third, and Q is the second letter, and T is the third. So it means BC and QT are also corresponding. Then the last, of course, A is the first letter and C is the last letter. P is also the first letter and T is the last letter. So AC and PT are corresponding, meaning AC here and PT here are corresponding. So that's how you can tell which sides are corresponding. Okay, here you might underrate the question or the figures given, because you can easily tell which ones are corresponding. But if PQT is turned, you can get confused. So if you have been given the question that they have stated the name of the figure ABC similar to PQT, just follow the letters. But it's not always that they will tell. They can just say the figures below are similar. Then you have to identify which ones are similar, and it can be tricky, but from the way the shapes have been drawn, it can be easy to tell. Okay, so how do you get the scale factor for such? You just have to get or to identify two sides which are corresponding, and they have given us the measurements for those two sides. Once you identify two corresponding sides that have measurements given, you can get the scale factor. So in short, you can get the scale factor by comparing all these. So you can compare AB and PQ, AB and PQ, also BC and QT, BC and QT, also CA and QT, CA and, no, this is a mistake, CA is supposed to be with PT here. Okay, so depending on what you have been given. Due to time, we're just going to take a look at one example, and yeah, after that maybe you'll be able to understand how to tackle such kind of questions. So the question says, given the diagram below, find BC. Simple. Or actually, this is the difficult scenario where they haven't stated which two sides are corresponding. To make matters worse, we can only see one shape here, but in fact there are two shapes. There are two triangles here, A, C, and E. Also B, C, and D. So there is this and there is this. Okay, so these two triangles are similar. Okay, so even identifying which sides are corresponding is easy because of the way they have been put. Here you can easily tell that this side corresponds to this side. This side, that is AC, corresponds to BC, and EC corresponds to DC. So the job is just to identify two corresponding sides that they have given us the measurements. In this case, BD and AE, they have given us the measurements. They are looking for BC, so it will be easy to find BC since we have BD and AE. Then the second question is area of triangle BCD. So area of triangle BCD, if area of ACE is 2 centimeters squared. So remember our K, in this case we have AC corresponding to BC, or CE corresponding to CD, or EA corresponding to DB. So I always advise to write all the corresponding sides. So just pick two sides that have numbers given. In this case, it's EA and DB, where they have given us 3 and 6. So we're going to use that to get our K. So we pick one with both denominator and numerator given. So the last one in this case. So K is equal to 6 over 3, which is 2. So the 6 is the EA and the 3 is the DB. So 6 divided by 3 is 2. So that's our K. So now they want us to find BC. So if we look here, where is BC? So BC is here. So for us to find BC, we need to have AC. Do we have AC? If we go here, we do have AC, meaning that this is this is going to make things easier for us since we have AC. So AC is 1. So we're going to pick this equation. Here where there's K, we're going to put 2. Where there's BC is what we're looking for. Where there's AC, we're going to put 1 since AC we have been given. So it's going to be K is equal to AC over BC. We're looking for BC. So K is 2, AC is 1, BC is the one we're looking for. So when you do cross multiply, it's going to be 2BC. And when we divide both sides by 2, it's going to be 1 over 2. That's BC. That's BC. Okay. Next, we go to the second question. Area of triangle BCD. So for areas, remember, we have to square the K. So K has been squared, K has been squared, meaning that our K is 4. So we're going to use 4. Okay. But which one is going to be on top when we're comparing the sides? Remember, K in scale drawing, it was map distance over scale map distance over actual distance, or map area over actual area, or map volume over actual volume. But in this case, which triangle, we're not working with the map and the actual thing. We're working with two similar objects. Okay, so in this case, we ask ourselves, how do they get K? So we got K by saying EA over DB. EA is the dimension for the larger triangle and DB is for the smaller triangle. So because of that, we are going to make sure that the area for the larger triangle is on top and the area for the small triangle is on the bottom. Okay, so just if you haven't gotten me, let me just say that again. When finding K, the formula we use was EA over DB. The side for the larger triangle is on top. So even when finding the area for the larger triangle should be on top. Then the side for the small triangle is on the bottom. So even when finding the area for the small triangle should be on the bottom. So we're going to have area of ACE over area of BCD. Okay, ACE is on top, area of BCD is on the bottom. So ACE we have been given, we're looking for BCD. So we're going to plug in. So K squared is equal to 2 over X. Where is the 2 coming from? The 2 is the area of ACE. The area of BCD is the one we're looking for. K is the 4 here. So we can continue like this. Okay, we can cross multiply. We're going to get 4x equals 2. We can divide both sides by 4. We're going to get 2 over 4. Reduce to always terms. We're going to get, or expressed in decimal, we're going to get 0.5 centimeters squared as the area for the smaller triangle. So this marks the end of this topic. Happy solving.